Morning. Hope you all can hear me today.
Morning.
How was your weekend?
Mine's good. Got to go visit friends and family and bottle some wine.
No, you got like interesting stuff going on. Chair building,
Yep.
wine bottling.
It should quiet down.
Well, my weekend wasn't that eventful. I guess just trying to get caught up on all the. I'm doing a lot of video editing for my other class because they're all online, and I'm basically taking last semester's Zoom recordings and then editing them down into shorter chunks. But that's a lot of work because for basically I'd say for every 10 minutes of video, it probably takes 20 to 30 minutes to actually edit it down. And that's like not doing anything really special. That's just cutting out the gaps and trimming it down. But you kind of like can't get away from watching it at least once or twice. So that, a 10-minute video takes 20 minutes just to kind of watch it, and then 10 minutes of actually doing the work. And I've been thinking like, should I get like a faster computer? And it's like, it's tempting, but that wouldn't really save a lot of time because I still have to watch the video, right? And the
Right.
Faster computer doesn't speed that up. The faster computer might help with things like rendering and saving the file at the end, but that's a relatively minor part of the whole editing experience, I guess, if you say. So, I don't know.
Would it work to watch it at like 1.5 speed?
No, it means like as I'm editing and doing things like cutting out little bits, I still have to like watch the video as it's going and then figure out where the gaps are that I need to cut out and what sections I can get rid of. So that's the part I'm talking about, watching it. Like, you just have to go through it at least once just to take out the portions you don't need. And then you kind of have to go through it again just to make sure you got everything right at the end. So yeah, it's just a lot of work, and so I'm perpetually behind on that. All right, well, let's see. For today, we were going to go over some more of the string functions. and then we could answer some questions about the CSI assignment. Actually, why don't we start with that? How are you doing on that assignment, and do you have any like nagging questions or challenges you ran into? Or are you done? That's always a possibility. Why don't you give me kind of like a little status update? Like, if you started on it, how's it going?
Well, I'm done. I got it.
Oh.
I got it going.
Goodness. Well, let's start with how many hours roughly did it take? Just ballpark, right?
It took probably 2 or 3.
Oh, okay. Well, that's probably that's pretty good.
Well, I mean, I've done stuff like that before, so I don't think I'm a good barometer for that.
Yeah, my experience has been that most students probably spend, I'd say the average is anywhere from like 4 to 10 hours, and it's a really big range, right? It's not like a tight range. It's some people get it pretty quickly, and some people spend a long time on it. One comment here was, I was able to get all the photos, but still a bunch of trash mixed in. Need to weed out the trash. Okay, so all the photos are viewable, but what do you mean by trash? Like, do you have extra files, or do you have like files that are like the wrong size? Files aren't ending correctly. So like the files are too big? Well, since people have started on this assignment, what was kind of your general strategy for finding the ends of those files? Like the naive strategy would be to start to find the beginnings, which is fairly straightforward to find the beginnings. But finding the ends is where the challenge is. And if you just scan forward from the beginning to look for that 2-byte sequence, about half the time you'll find the end that way. But the other half of the time you'll actually find that 2-byte sequence somewhere in the middle of the file, and you'll kind of prematurely mark that as being the end of the file. So you need to find where the actual ending one is.
Well, what I did was when I found the beginning, then I would look from the end of that 512-byte block and look for the end. And if I didn't find it, then I'd go to the next block and start at the end and look for that 2 bytes. If I didn't find it, then I'd go to the next block. So I'd keep going to the next block, look for the last occurrence of those 2 bytes, and then I check to make sure there was a 0 after it, since in this case we know there's always a 0.
Okay, so let me see if I can draw a picture of what you're doing. So if each of these squares represents one of the blocks, then you find that 4-byte sequence, which starts
We're
here.
seeing your code. We're seeing your code, not the drawing.
Here we go. So you find that 4-byte sequence, right? And then you said you like would skip to the next block.
Well, first I'd look at the end of that block just in case it's tiny.
Oh.
Tiny.
So let's be more specific about what you mean by you look at the end. Like, do you look at the last 2 bytes?
No, I start at the end.
Mm-hmm.
So I set a loop to start at the end of that 512-byte block and move backwards until it finds those 2 bytes or doesn't.
Oh, I see. So you're scanning kind of backwards.
Right.
And you're looking for that 2-byte sequence. And if you
right.
and if you get all the way to the beginning of the block and you never find it,
then I jump to the next block. So I have a pointer to
Then you jump to the next
the
one,
next block, and then I go backwards from
and
there.
then you start scanning backwards again until you reach the beginning of that block.
Right. And if I get there, then I know that block's part of the image and go on to the next block.
Okay.
And then eventually find those 2 bytes.
Okay, so let's say you find them here.
Right. Then I know my image goes from where I found the 4 bytes to the end of those 2 bytes.
Okay. So how do you know you're not finding those 2 bytes that are in the middle of the image?
If I'm going backwards and I find something that's not let's see. I'd have to look at the code. If it finds other bytes that aren't zeros, then I know I'm still in the image. Is that right? Let's see. I'll have to pull up my code.
So when you're scanning backwards, are you just looking for that 2-byte sequence?
Well, okay, I think I am still semi-awake, so let me give me just a second to pull up my code.
So what we're trying to address is when we find that 2-byte sequence, which marks the end, how do we know that's at the end of the file and not one that's in the middle of the file? And so this is, I think, a fairly good strategy. There are other strategies, but your strategy is to move forward through the file, 1 block at a time, go to the end of each block, and then scan backwards looking for that 2-byte sequence. And you mentioned earlier something about once you find that 2-byte sequence, you check to make sure there's a 0 after it.
Right, because let's see. Okay, yeah, so when I'm scanning backwards, I'm just looking for that 2-byte sequence. Mm-hmm. So I'm looking for the last occurrence of that 2-byte sequence in that block.
Okay.
And then once I find it, then I look at the byte after that to see if it's a 0. And if it is, then I assume I found the end.
Okay.
But I guess that wouldn't work if there was somewhere in the image where there's actually the 2 bytes followed by a 0. Mm-hmm. I don't know if that can actually happen in a JPEG.
It probably could.
It probably could.
But maybe it just doesn't for ours.
Right.
I'm curious to know, how many images did you find?
I found 6.
Ooh, there's more than that.
There's more than 6. All right.
Yes.
Well, then I need to work on it some more.
Kai says he found 29.
Wow.
Yeah.
All right. Well, my algorithm doesn't work.
I think you're on the right track.
Okay.
Now, so what are some other strategies that have been used? Maybe Kai's got something. Kai says his is similar. This is a great assignment, right? Because you came up with 6, and other people come up with 29, and it's kind of like I didn't tell you how many there are. So it's kind of that's part of the puzzle, is figuring out whether you've got the right number or not. Okay, so it looks like Kai's strategy is once you figure out, well, I think what he's doing is he's finding the 2-byte sequence and then look at the start of the next block and see if that contains the starting sequence. So find the 2-byte ending sequence, assume that's the end of the file, look at the next block and see if the start sequence is there. And if it is, then this must have been the ending block, if I'm interpreting your description correctly. And for that, you managed to get 29 images, but you said there's some extra stuff at the end. So I think that's a pretty interesting strategy. So I guess maybe scan forward until you find that 2-byte sequence, then look at the next block and see if it contains the start sequence. If it doesn't, then you probably aren't in the, you're not at the end of the file, you're somewhere in the middle. So keep scanning forward until you find another 2-byte sequence, look at the next block, see if that contains the start, and if it doesn't, keep going. So I think that strategy probably has one issue with it, and that is it assumes that the ending of an image and the start of another image are going to come in blocks that are right next to each other. And I think that there are some places in the SD card image where there may be multiple blocks between the end of one image and the start of the next one. Like an image might end here, and then the next one won't start until like over here. And in that case, what would happen then is you wouldn't correctly identify this one as being the end of the file. You would then keep scanning forward until you found a situation where you had the ending marker right next to a beginning marker, which actually might take you well into the next image and the image after that, until you finally ended up in a place where there were the ending block and the beginning block right next to each other. And maybe that's what you were talking about, how some of the files have extra stuff on the end. So think about a situation where the ending block and the starting blocks aren't next to each other. How could you cope with that? And you probably discovered that even if your files have extra stuff on the end, even if the files are too big, they still view correctly because the JPEG viewer is basically leapfrogging its way through the file to find all these little section headers. And when it finally encounters the real end of file marker, it just stops and it ignores everything that's beyond that. So the images still view correctly, even though they're too big. But it would be nice to kind of get the files down to as close as you can to the correct size. So does anybody else have a strategy that seems to work? Thinking about it? I'm in a little bit of a pickle here because on Wednesday I have to not do a live session again. I have another meeting to go to. Actually, it's not a meeting. It's where I'm evaluating another one of the faculty. And so their class is exactly at the time as my class. So unfortunately, I have to do a rerun of a stream again. And what I might do, as far as a rerun goes, is I'll either just replay the one from last year in which we go over the CSI stuff, or I could kind of cobble together a kind of a hybrid video that has some hints about doing the CSI assignment. Let you maybe work on it a bit more over the next couple of days and see if you can find a better strategy for finding the end of the files. What do you think? So should I kind of give you a good strategy now and you can implement that, or should we wait a couple of days and then see if you find something that works a bit better? What do you think? And the strategy I would give you today is not like the strategy, but it's one that works pretty well if you can implement it correctly.
Well, I wouldn't mind a couple more days to come up with one.
Okay, a couple more days. So what I'll do is I'll find a couple of the videos from last semester that have more hints about the assignment in it, and I'll put that together. That's what you guys can watch on Wednesday or anytime you want. So let's turn our attention to the string functions that we were writing last time. One of the first functions we wrote was the string length function. And here's how it works, in general. We start with a counter at 0. And then as long as the ith character of the string is not the null character, so we're scanning forward until we hit that null character, we're going to increment I. We're going to keep track of the number of characters we've seen and our position within the string. And when we finally hit that null character, we just return the value of I, and that tells us how many characters we saw. So the first thing I want to do, and I kind of hinted at this last time, which was there are ways that we could tighten up this function so that it works the same, but the code itself is shorter. And the first thing that we could do here is recognize that the null character's ASCII value is 0. Just like the ASCII value of the letter A is 65. And in fact, you could put in, whenever you're doing character comparisons, you could just put in the ASCII value. You could just put in the number, and it's the same as putting in the character. Like over here, where we did count uppers. Instead of using the character A, we could just put in 65, and it would work exactly the same. And instead of the letter Z, the character Z, we could just put in 97, or whatever the ASCII value of Z is. And this function would work exactly the same. It's a little clearer to use the characters, I think, when you're dealing with characters, but you could just put in the numbers. So over here, we don't have to put in the character, the null character. We could just put in the number 0, and this function should work exactly the same. Let's go find the place where this is called, which is right here. And I'm just going to comment out the rest of the program. So it says the length is 12, which is correct because we got 5 here, 5 here, we got a space, that's a total of 11, plus we have the newline character, which gives us a total of 12. Okay, so we can replace this with a 0. And so what we're saying is, while the ith character is not a 0. And as we pointed out before, there's no such thing as a Boolean in C. There's only just numbers. And if a number is 0, it's considered to be false. And if it's not 0, it's considered to be true. So what we're basically saying here is, while the ith character is true, what we're implying is that it's not equal to 0. So really, we could actually just get rid of this comparison against 0. We could just say, while the ith character is not 0, right? So we're going to look at the ith character, we're going to get its value, and if that value is a 0, then this condition will be false and it will jump out. And if this value is not 0, this condition is true and it will continue, it will do the body here. All right, so you see that? So whenever you're doing a comparison against 0 or not 0, you can really just take away the actual equality comparison or the inequality comparison and just look at the value itself. So it still works the same.
So does that, do you think that changes what it compiles down to, or?
No.
Yeah, okay.
It compiles exactly the same.
Okay. It's just shorter in C.
Yeah.
Okay.
I mean, you can do that for any place where you've got an if or a while, any kind of condition. If you're just comparing against 0 or not 0, you can just do the value itself. If you want to compare it against you know, like while it's false, basically, you just put a not in front, and then that works as well. The other thing we can do to this is recognize that all of these variables, I and s, are local to the function. Obviously, we can change the value of I, and it doesn't affect anything outside the function. But we can also change the value of s, and it doesn't change anything outside the function. So here's something we can do, and this is going to look a little wacky here. Let's just look at the thing that s is pointing to. Remember, s is just a pointer to a character. In this case, when it gets passed in, it's a pointer to the beginning of the string. But s itself is just pointing to a single character. So I can dereference s, and it will tell me what s is pointing to. So while the thing that s is pointing to is not 0, increment I, and we can also increment s. So what are we doing here? So we've got this string, and let's say it's hello, and a null character. And we've got s, which is pointing to the first character in that string. And so we look at what s is pointing to, and if that's not a 0, we're going to increment s. We're going to make s point to the next letter. And then we ask, if that thing is not 0, then we increment s. And so s is going to keep kind of moving forward through the string until it points to that null character. And then when it is pointing to that null character, the condition becomes false and it jumps out of the loop. Okay, so that's what's going on here. Does that kind of make sense to you? So as long as the thing that s is pointing to is not equal to 0, increment s. We also need to increment I to keep track of how many characters we found, but we're going to increment s. Let's see if that works. I just saved it, compile it, run it, and it still works. Does this compile down to exactly the same thing? Yeah, it probably does. Oh, what else can we do to this? Now, I'll have to say, once we get to this point, this is probably as far as most C programmers would go. They might go one extra step, But when you're dealing with strings, this is actually a fairly common way to deal with them. Rather than using array indexing into the string, you just use pointer dereferencing and pointer arithmetic in order to move your way through the string. Now, here we're incrementing s. We're using the s++ operator. And do you know there's a difference between ++s and s++? Do you know what the difference is?
Well, the ++s increments s before it looks at the value,
Right.
and s++ looks at the value and then increments.
Yes. So one's called the pre-increment and one's called the post-increment. If it's standing by itself, like it is here in the program on line 10, they're equivalent. But if you embed the ++ inside of an expression, then what the computer will do is, let's say you use s++, use post-increment, then what it will do is it'll evaluate the expression and then it will increment s. First, before I make any more changes, Kai pointed out that using the array indexing is exactly the same as using pointer arithmetic here, s plus I, and then dereferencing it. So s bracket I is equivalent to s plus I dereference. These are the same thing. Okay, so take a look at this. So it's going to evaluate what s is pointing to, and then after it has looked at what s is pointing to, then it will increment s. And it still works. Kai says, that works? Yes, it does. So it's kind of weird. I'm putting the increment inside of the condition for the while. But remember, the increment happens after the condition was evaluated. So it's going to evaluate the condition and then do the increment. So yes, that works. And now that we've only got one thing inside of the braces here, I can get rid of the braces. And that doesn't change anything. And also, since I got rid of the braces, I can also move the I++ up next to the while loop. And so what do you think about that? Let's just make sure that still works. Tell me what you think about that. Yep,
It's pretty bizarre.
still works. Is it, you think it's bizarre? But once you get used to seeing this kind of notation, it's really actually very straightforward. So while the thing that s is pointing to, increment I and also increment s.
It definitely takes more thought to figure out what it's doing if you're not already used to it.
Yeah. I'm curious about something. So there's a built-in function called string length, strlen. And different operating systems, different compilers, have their own versions of that string length function. You see, there's a bit of history there. Long time ago, the very first versions of Unix, the operating system, along with the C compiler, were developed at AT&T Laboratories. This was back in the 70s. And so AT&T owned the rights to the Unix operating system and all the stuff that came with it, including things like the C compiler and the standard libraries. And so if you wanted to run a Unix system, you had to pay AT&T a royalty fee to be able to use their software. Now, in this day and age, it seems weird, right, with the free software and things that are available for very inexpensive. But back then, that's how companies that were in the software business made money, was basically selling a license to use a particular piece of software. So things like the string length function, although it seems really easy and obvious how to write a function like that, it was copyrighted. And so you couldn't write an identical function. If you wanted to implement string length yourself, and you either had to do it in what's called a black box environment, which is you don't look at the source code that anyone else has written to ever write that function, and you write it yourself from scratch, and you document that you never saw anyone implement that thing. Or you did it differently. You figured out some other way to calculate the length of the string that wasn't identical to what AT&T did. And so what you saw here was we just came up with like 3 or 4 different ways to do it, depending upon whether you use the array index or you use pointer arithmetic or whether you increment s inside the condition or outside the condition. As long as you make a couple of non-obvious changes to it, you should be safe from the copyright lawyers. So along comes things like Linux and BSD Unix in the 1980s, and they want to provide like a freely available alternative to AT&T Unix. And so they're now tasked with the job of implementing all of these C functions, but either not looking at the original source code at all or implementing it differently. And so it's interesting to look at different implementations of this and see how they went about doing it. Let's take a look. Let's just do a little Google searching here. Let's search for string length source code. And of course it would be in the stringlength.c. And let's see what this one does. Huh, that's a lot of code. I have no idea what this is doing. Oh, I think I know what this is doing. This is a very, very non-obvious way to calculate the length of the string, but taking advantage of the fact that most processors could look at 4 bytes at a time rather than 1 byte at a time. So it's basically loading in the string 4 bytes at a time and then checking to see if there's a null in any one of those bytes using some bit manipulations. This allows it basically to calculate the string length, but roughly like 4 times faster. Okay, I'm not interested in this solution here because this is totally different than what we're doing. But let's take a look at the one from Apple. Here it is. Okay, forget about this register thing here. Basically, we have a pointer to a string right here. And then we have another pointer called s. So we have str and we have s. And so what it does is it assigns s to be str. So s and str are pointing to the same thing. Let me see if I can draw a picture here in a moment. Then it looks at the value of s, looks to see what value it's pointing to. If it is 0, then it will jump out of the loop. And if it is not 0, it will continue the loop. And then it increments s. Remember, the for loop is just a while loop that's been kind of condensed down. So this is the initialization, this is the condition, and this is the increment. And then it returns s minus str. Huh, interesting. So what this is doing is we've got this string, And initially s and str are both pointing to the same character. So that's what this does here. Make sure that s and str are pointing to the same character. And then it starts moving s forward. Okay, so this pointer here starts moving forward, 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 until s is finally pointing at that null character, and then the loop stops. So at the end, you've got s pointing to the end of the string and str pointing to the beginning of the string. And then what do we return here? We return the difference between s and str. Remember, those are just addresses, so if you subtract them, you're going to get the length. Right? Like if this is 5,000 and this is 5,005, then when you subtract them, you'll just get 5. Well, that's kind of cool. Let's see if we can implement that ourselves. So let's make a character pointer called beginning. Let's call it BEG. Actually, I'll call it start. So I'll say start is equal to s. And then I'll say while s is not pointing to the null character, increment s. And then return s minus start. Okay, so initialize start to point at the beginning of the string, and then start moving s forward until it hits the end of the string, and then return the difference between those two addresses, which should give you the length. It works. You still get 12. There was a question is, why don't we just return s? Why do we have to calculate the difference? Because s will give us the address of the end of the string, and we don't want the address at the end of the string. We want the length of the string. So we do need to keep track of where we started, and then we need to keep track of where we ended up, and then subtract the two to give us a difference. Okay, so that's one way to do it. Let's see. Oh, this is basically the same. Actually, this is pretty much exactly the same. So let's not look at that one. Oh, this is the one that does the 4 bytes at a time. I don't want that one. Ah, that's terrible. Again, 4 bytes at a time. Here's another one that also does the beginning and the end, but notice here there's nothing in the initialization section of the for loop, because that was done up here, and here there's an explicit check to the null character. So it's basically the same function that we wrote. It's just been kind of juggled up a little bit so that it doesn't look exactly the same. Right? So we got a null initialization section, we got an explicit check for the null character, and we got different variable names. And so it's just different enough that it might avoid any potential like copyright violation problems. Okay, here's a slightly different implementation. We still got the string, the S that points to the beginning of the string. We have the end of string, which initially points to the beginning. And then we move the end of string forward. So rather than S being used to keep track of where's the end of the string, S is being used to keep track of where's the beginning of the string. And then we have another variable, the local variable, that moves forward. And then we've got the post increment here. But the problem here, not the problem, but the issue here is that it's going to evaluate what EOS is pointing to, and then it's going to increment EOS. So it's going to increment EOS even when it's pointing to the end of the string. In the other versions, we only incremented the end of the string if the condition was still true. But by putting the post increment in the condition here, it's going to increment it regardless of whether it has hit the end of the string or not. So when you do that subtraction at the end, you also have to subtract one more, because now EOS is going to be pointing actually one character past the end of the string. So again, a slightly different implementation that accomplishes the same result. So it's kind of interesting to see all these different implementations that do this, that implement the same behavior, but in slightly different ways. And that's what black box reverse engineering is all about. Is you treat the thing that you're trying to duplicate as a black box. You can't look into the box, but you can feed things into it, and you can get results out of it. And as long as you implement that behavior and you don't look inside the box, then you can essentially reverse engineer. You can figure out how that thing works without actually looking at the code itself. And so all these people have come up with different ways of implementing string length that don't do it in exactly the same way, but have the same behavior in the end. So does that leave you with any like nagging questions? Now last time also we wrote this function called find or that looks for the letters OR next to each other within a string, and then it returns the index of the first one that it finds. And someone pointed out last time that if you have more than one, this is not going to find it, and that's absolutely true. If you have more than one instance of OR, it's only going to find the first one and then it's going to stop. In most of the cases, that's actually how these functions behave, is it just finds the first instance. If you want to find all the instances, then you've got to do something else. You've got to like find the first one, and then basically pick up where you left off and find the next one, and then resume where you left off and find the next one until you finally find the last one. So oftentimes there may be a pair of functions, one called find that finds the first one, and maybe one called find last that finds the last one. Works from the other direction, so it works from the right-hand side and goes towards the left. But there generally isn't really functions to find all of them. There's only find first or find last. But nevertheless, we have this function called find or, and it returns the index of where the O is within the function, or it returns -1 if it didn't find it. But I want to suggest to you there might be a different way to do this. It kind of accomplishes the same thing. It finds OR, just the thing that returns is different. So instead of finding the index of where OR is, let's have it tell us where that string is. Let's in fact let's have it return the address of where that OR is. So instead of returning an integer, it's going to return a pointer. Let's call this find OR pointer. We're still going to give it a string to search through. But instead of returning an integer, we're going to return a character pointer. So instead of finding Well, let's give us a new string here. Hello world. So instead of telling us what's the index of this O, it's going to give us what's the address of this O. Well, we still have to start from the beginning of the string and go to the end of the string. So this is going to be basically the same here. Actually, most of this is going to be the same. So I'll just copy and paste this code. But instead of returning I, I'm going to return the address of the O. So I'm going to return the address of the ith character of the string. And if we don't find the OR, I can't return a -1. What I have to do is return some kind of address, some kind of pointer that indicates that there was an error. If you were a Java programmer, in this case, you'd probably return null, which is just an invalid reference, a reference to nothing. In C, we can do the same thing. It's called null, but it's all capitalized. Okay, so it's basically the same function we had before, but instead of returning the index, we're going to return the address of the ith character of the string, or we're going to return null if it wasn't able to find it. So let's go down to our main, and here's where we call find OR right here. But now we're not going to be able to print out an integer. We're going to have to be able, what we can do is we could just print out the string that we got returned. Okay, because we get back a character pointer. Character pointers are basically strings, so we're going to use %s to print that out. What happened here? It says we have an ending comment character, but not a beginning one, so I got to put one here. There we go. All right, look at that. It says found OR at ORLD. So it gave us back the address of where the OR is, and we can treat it just like a string. So what we're getting back is not a new string, it's just the address of where the OR is within the original string. So let me say that again. What we got back from find OR pointer is not a new string that contains those 5 characters. It just contains the address of where the OR is within the original string. So str points to a string that starts at, let's say, address 5000, and what this returns is like 5008. So it's still within the original string. And this is actually what a lot of the functions in the string library return, is not the index. Some of them do return the index, but most of them, when you're looking for something, they don't return the index. They return the pointer to where it found that string. In fact, we could generalize this a bit to not find the letters OR, but to find a substring within a larger string. Let's go ahead and let's write that function. Let's call this search, and it's going to return a character pointer, and we're going to pass it 2 things. We're going to pass it the string that we want to search through, and we want to pass it the string that we're searching for. So I'll call the first string str. This is the string we're searching through, the longer string. And then target is the string that we're searching for, the one that we're trying to find. So it's going to look a lot like this find or function that we just wrote, except that we're not going to be looking for O and R. We're going to be looking for the individual characters within the target. So let's start this kind of the same way. Let's go int I equals 0 and int length equals string length, actually string length of str. So what we're doing is we've got str and we have target. What we're going to try to do is we're going to take our target here and we're going to try to match it up against the letters of the string. And if these don't match, then we'll take that target and we'll kind of like move it forward, and then we'll try to match it up. And if those don't match, we'll move it forward again and then try to match it up. And we'll keep moving this target forward until it finally does match. And then we've found the string that we're looking for. And we're not going to physically move the target forward. All we're doing is we're going to match it up with these, and then with this pair, and then with this pair, and then this pair, and this pair. And we're just going to keep trying to match it up as we go down the line until we finally find it. So just like with the find or, we are going to do a loop that starts I at 0 and then goes to less than the length. And we did length minus 1 here because the OR is 2 characters long, and we want to make sure that the OR doesn't fall off the end of the string here. So we'll go while I is less than length minus, well, we'll figure that out in a moment here, but let's just put 1 for a moment. And now we need another loop that's going to look at the individual characters of the target string and try to match them up against the source string. So we got one outer loop that's moving our target string forward, and then an inner loop that needs to look at the individual characters of the target string. So let's go like int t equals 0, and then we'll say while star, how about it, while the ith character of the source string is, well, so let's see, what do we need to do here? We need to look at the target string and match up each of the characters against the source string. And as long as the ith character of the target string is equal to the ith character of the source string, then we move to the next letter of the target string. And when they aren't equal to each other, then we know we haven't found a match. So as long as they're equal to each other, we continue to match characters. And when they're not equal to each other, then we fall out of that loop. And we know that we didn't find it, and we can now move to the next position in the source string. So while the ith character of the source string is equal to the t character of the target string, This would be I plus t, actually. Then we'll move t forward. Okay, so we'll look at the t character of the target string and compare that to the I plus t character of the source string. And if those are equal to each other, we'll move t forward. So if we got all the way to the, gosh, this is trickier than I thought, because we got like a whole bunch of like different issues here. Like, what if we get to the end of the target string? Like, how do we detect that we got to the end of the target string? And also, what if we fall off the end of the source string? Golly, there's a lot of stuff going on here. This is, okay, so while these are equal to each other, increment this. And we need to detect that we got to the end of the target string too. How about this? Let's put that in the body of this here. And we'll say if the, oh, that's not going to work. I was going to say if the target t is equal to null, then we know we hit the end of the target string, and therefore we've matched the whole target string. But that's not going to happen because, oh, I guess we should do it like this, t plus plus. Then we'll say if target t is equal to null, then we found it. We can say return address of S sub I. I think that's right.
Would that work if the target was at the end? Because then S of I plus t would be null and target of t would be null.
So then they would be equal to each other.
And then it would increment t, so then target of t would point to the whatever's after the null, right?
So you're talking about like, what if our string was like rotor, and we're looking for or, and they're right here at the end of each other, right?
All right.
So then these two end up being equal to each other. So we increment t to point to the next one. So do we have to put an additional condition here to say while?
Yeah. Well, target of t. And
so while basically while this is not the null, while this is not 0, and these are equal to each other, increment t.
Right, because that would tell you if you got to the end of, it would stop when it got to the end of target, right?
Right. And then if it is equal to null, then return the address. So we got all the way to the end of target, that we were able to find it. And then if we got all the way to the end of this loop here, that means we didn't find it. Boy, I hope that's correct. And then here, this is not supposed to be -1. This should be the length of the target. And that way we never end up in a situation where our source string and our target string overlap at the end. Right? I don't want to end up with this situation where this is like coming off the end like that. I want to make sure this stops when the two of them are lined up on the right-hand side.
Does that need to be target length -1?
It might be.
Because when we had a 2-character thing, it was -1 in
Yeah.
parentheses. Target length -1 in parentheses, I think. Or does that matter? No. Yes.
Okay, so let's test this out. So we're going to enter a string, and let's have it search for, the. Found the at %s. Search through our string, and we'll search for the. This should have been str. str. There we go. Okay, enter a string. Let's search for something that doesn't contain the. Actually, let's have it contains the towards the beginning of it. So it could be, what should I use? It could be just something junky and then junk, right? There it is. Uh-oh. We ended up in an infinite loop. So I'm going to press Control C. Let's go a bit simpler than that. Let's put the at the beginning. Okay, that worked. So it found the at the beginning. Okay, so let's try this again. Let's do one character and then the. And that gets us into an infinite loop. So what's going on here?
Oh, we're not incrementing I.
Oh.
And I'm not sure that while is, I think target length -1 should be in parentheses.
Okay, we can
right, because when we had a 2-character string, we were subtracting 1.
Okay, that looks like that worked there. So I found the 1 character after the F. Let's go to this. Looks good. And then let's put it at the end. So far, so good. And then one thing to try would be like just put th at the end. And it didn't find it. How about th, 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 e? That looks good. All right, so there's roughly some kind of string search function. And there are ways to make this faster. If you're searching through long strings with also long target strings, doing it the way that we've got it is really actually very slow. Like, let's say the string you're searching for is 100 characters long, or the string you're searching through is 100 characters long, and the string you're searching for is, let's say, like 20 characters long. Then you end up matching the 20 characters of your target string against 20 characters of the source string. And then if you don't find it, you have to move it forward by 1 character and then compare 20 characters of your target string against 20 characters of your source string. Of course, you're going to stop when they're not equal to each other, but you're looking at worst possible case. So the worst possible case is all the characters are the same, except the last character is different. So you end up having to like search over and over and over again. And the running time to this is roughly equal to the square of the length of the target string. But there are actually ways to make this go faster. One of the ways to make it go faster is start at the end. So you move the target string all the way to the end, and then you look at the last character. And if those don't match up, then you can immediately not just move it one character forward, but you can actually move it the entire string length forward. So you can make it jump forward as you go down the string. And so that's called like the Boyers-Moore string searching algorithm, in which you make jumps going backwards. And that makes it go a lot faster. And then there are also some other tricks you can do, like we saw with the string length function. You could load in 4 characters at a time and then just compare integers. And if the integers are the same, then you know you can move to the next 4 characters. So there's things you can do with that as well. But this is basically the technique here, is doing a character by character comparison as you move down the string. Okay, questions about that one? So I want to do one more, and we had this trim function from last time that would find any white space characters at the end of the string, and then it would basically look for the first non-white space character and then put a null right at the end of that, so that we would essentially eliminate all of the white space characters. So as long as it found a white space character, it will replace that white space character with a null, effectively truncating the string to the first non-white space character. But let's write a different version of this, that instead of trimming off all the white space characters, it just trims off the newline character. The usefulness for this would be, let's say you're using fgetS to read input from the user, and you know that when you press the enter key shows up in the string, but you just want to get rid of that. Let's call this trim NL for just trimming the newline. So this one's fairly easy to do. What we have to do is search for that newline character and then just replace it with a null. We could either start at the end of the string and then go backwards until we find the newline character, or we can start at the beginning of the string. We know there's only going to be one, because the user just types in their string and they press the enter key. So we know there's only going to be one. So we could scan forward from the beginning of the string, find that newline character, and then just replace it with a null. Let's see if we can write that using pointer arithmetic. So we have this character pointer s that's pointing to the beginning of the string. And we can say while star s is not equal to the newline character, then move s forward. So this is going to start at the beginning of the string and move s forward until it hits that newline character, and then it's going to stop. So once we have found the newline character, what do we do with it?
We put a null there.
Yeah, so we'll just replace it with the null character. So now s is pointing to that newline character, so all we got to do is just say put a null character where s is pointing to. So let's come down to our main, and after we enter the string, let's just call trim NL. And this is declared to be void, so that's good, because it's not returning anything, it's just modifying the string. So remember before this was returning a length of 12 because of that newline character. Now it's returning a length of 11. That's exactly what we wanted. And it doesn't have that extra newline character. It doesn't have that blank line that was there before. So this is going to retain all the spaces that we type in, including the ones at the end. It's just going to get rid of that newline character. But we do have one issue that we need to bring up, and that is, what if the string that we are trimming doesn't have the newline character at all? This could happen in a couple of situations. One is if I pass it a string that happens to not include a newline character, like I've already trimmed it, and now I'm calling trim NL again for some reason. It's not going to have that newline character in it. And the other reason this might happen is when you call fgetS here, you pass in the maximum length of the string. Here it's 100 characters. If the user types in more than 100 characters, it will stop at the 100th character and just give you back that string. What that means is the newline character the user typed is still out there waiting to be pulled in from standard input, but it's not going to be in the string that fgetS returns to you. So if you call fgetS and the user types in a string that's longer than the maximum, it won't have the newline character either. So there are some very legitimate reasons for taking into account that the trim function might not encounter a newline character. And how do we do that? How do we get it so that it only replaces the newline character if it is there? And if it's not there, it just leaves the string as is.
You could put a test after the while to see if start S is newline.
So you mean like in the line below or somewhere in this condition?
Well, after the while, so between those two lines.
Here.
Yeah. So if star S, would that work?
No, it's not going to work because
no, because that's still going to go off the end of the string.
Right. If it doesn't find the newline character, it's just going to keep incrementing S.
Right. So in the while loop, in the condition, yeah, while star S and star S is not equal to N. So then if it hits null, it's going to stop.
Mm-hmm.
And then you can leave that second line because it's already null and you're just setting it to null again.
Okay, that's fine. So as long as star S is not pointing to a null character and it's not the newline character, increment S. So when either of these conditions becomes false, right, if either it's pointing to a null character or it encounters the newline character, the loop is going to stop. And then we just replace whatever character that is with a null character. I think that's fine. So still seems to work. The thing to do would be, let's call trim NL on a string that does not contain a null character. So let's maybe come down here and we'll go character string 2. And then we'll call trim NL on string 2. And then we'll just make sure that it didn't trim anything off. Did it work? Oh yeah, here it is. Here's my string. Not trimmed. That's good. So that's a fairly handy function to have. Something that trims the newline off if it's there and doesn't trim it off if it's not there. So this might be a good time to go and actually look at the string functions themselves. Let's take a look at what the string.h header file includes. So there's some functions for doing memory copies. Let's ignore those for now. But here's string cat. It takes two strings, a destination string and a source string, and sticks them together. What it does is it takes all the characters out of the source string and puts them onto the end of the pre-existing destination string. So it is a little strange that the destination comes first, but that's something you got to get used to, that in the string functions, usually the string that you are kind of affecting is the one that comes first, and any additional stuff comes after that as far as the arguments go. Then there's string ncat that does the same thing as string cat, but only does the first n characters of the string. There's string char, that searches for a character within a string and then returns to you the address of where it found it. So it's kind of like the search function that we wrote, but instead of searching for a substring within a string, it just searches for an individual character within a string. So it's searching for an individual character and then returns the address of where it found that character. String compare is used to compare two strings, and it will tell you if those two strings are equal to each other, less than, or greater than to each other. What you cannot do is you cannot use the equals operator or the less than operator or the greater than operator, because those will not be looking at individual characters within the string. They're going to be looking at addresses. And what you're asking it is, are the addresses of these two strings equal to each other? And they're not likely to be. So you cannot use the equals, less than, or greater than operators with strings. You need to use string compare. String n compare does the same thing, but only looks at the first n characters of the strings. String collate is similar to string compare, but takes into account language differences. Like a string compare just works with ASCII characters, whereas string collate understands more about foreign characters. String copy takes all the characters out of the source string and puts them into the destination string. String ncopy just copies the first n characters of the string. I don't know much about these other ones here. Here's string length. We wrote that one ourselves. String r character, which searches from the end of the string and looks for the first occurrence from the end, so from the right-hand side. String, this is kind of what we did for the search function, is it looks for a destination or a target string within a source string. So we wrote that ourselves, and then it returns the pointer to where it found that string. String token, which is used to break up a string into smaller substrings by using a delimiter. Okay, so we looked through all of those string functions, and we could actually rewrite our trim function to use these. Which one of those functions do you think would help us write that trim function? Remember, the first thing our trim function had to do was find that newline character, and the second thing it had to do was replace it with a null. So do you think any of these could help us?
We could use that stir chur to find newline.
Exactly. We could use this one right here to find that newline character. So we'll pass it s, the string we're searching through, and the newline character, and what it returns to us is a pointer to where that newline character is. Or it returns null if it couldn't find that character at all. So what we want to do is replace that newline character with the null character, but only if it's actually pointing to the newline character. So it's basically the same as what we got here. So we'll put a check in front. We'll say if star NL is not null, then go ahead and replace the thing it's pointing to with null character. So we're going to call string character, find the newline character, and get its address back. And the address will either be a valid address or it'll be null. So if it's a valid address, go ahead and replace it with the null character. And if it's not a valid address, don't do anything. So this is a pretty good version of trim that doesn't do a loop on our own. We're just going to use the loop that's inside a string character, and then we just checked its return value. And the reason I'm pointing this out to you is because throughout the rest of our assignments, from basically here on out, anytime you get user input from the user using fgetS, you're probably going to want to trim off the newline, and this is a really quick and easy way to do it. You just use string character to find the newline character, and then replace it with a null character if you find it. So you can make a function out of it, or you can just put those 2 lines of code right into your input code right below the fgetS to just trim off that newline character, if it's there. Okay. So let's quickly go over what we did today. We wrote, or I showed you initially, how to rewrite the string length function to use pointer arithmetic rather than array indexing. Then we ended up rewriting find or to return a pointer rather than an index. And the usefulness of this, which you saw later on when we were searching for that newline character, but another usefulness for this is we could now use this to help us find all the occurrences of R. See, what we'll get back is a pointer to the first one. And then we can just call find or again, but feed it the address of where that first one was, and then it will basically resume searching from that point forward to find the next one. Actually, we don't return the address of where the OR was. We return the address +1. So it starts searching at the next character, and then it searches to find the next one. And then we can and it returns the address of that one, and then we can call find or again and have it resume to search from that point and find the next one. So we can use this one to wrap it inside of a loop and find all the occurrences of OR. And then we wrote a function for trimming the newline characters off of the end of strings. Oh, before we did that, we wrote a search for doing a substring search within, so search for a target within a string. And that also returned a character pointer, returned a pointer to where it found the string. And then finally, we wrote 2 versions of trim NL to trim the newline characters off of strings. One that relies on the built-in string functions, and one that just uses our own loop. Okay. So as I said earlier, on Wednesday, I'll have some kind of video for you to watch because I won't be here again. I hope this will be the last time in this semester. And then we'll be back again the following Monday to start on a new set of topics. And just a little preview. We've been turning in assignments using just by basically downloading the C file and then uploading that to Canvas. But what if your project contains multiple files? Sure, you could zip them up and give them to me. But there's another way to do it, which is to upload those files to what's called a repository. And then from there, I can just download the files. And that has a couple of advantages. One is it can keep track of changes for you. Who among us have not tried to fix a bug in our program and end up making the program worse? It'd be nice if we could roll back to a previous version, and version control systems give us the ability to do that. It can take a picture, essentially, of your program as it is, at that moment, and it saves a snapshot of it so that you can roll forward and backward through time and retrieve previous versions, or roll forward again and retrieve not future versions, but versions, in the future from those past ones. So you can basically move a time pointer back and forth. Boy, I wish we could move it in the future, right? I would just roll it forward to when the assignment is done. But version control systems give us the ability to take snapshots and keep those snapshots. And they also give us the ability ultimately to collaborate with other people. So 3 advantages there. One is you can upload your files and make backups on a remote repository. 2 is you can collaborate with other people. And 3 is you now have the ability to keep track of versions of your programs. You can go back in time and see what it looked like in the past. So I'm going to be introducing that to you next time. And then we'll start on some new stuff, right? I think we're going into a unit where we're going to start learning how to crack passwords. So I'll show you how passwords get stored on a computer system, and ultimately how hackers go and download that database and then write programs to try to figure out what those passwords are. So they're able to essentially decrypt the passwords. So it's going to be an exciting section because we're going to write the kinds of programs that professional hackers write, just that ours is going to work on a smaller scale, but basically it does the same thing. So I think it's really relevant and really interesting stuff to study. So the next time that we will have a live session will be next Monday. So Wednesday, for those of you who are in my class, I'll just be posting a video of a previous session. And then on Monday, we'll have our next live session. Okay? So that's it for today. I hope this was interesting for you. If you haven't started on that CSI assignment, please do. Oh, one last administrative thing for my students is I have posted a week 6 survey for you. Go find that in the modules. And they need to complete that by the end of next week. And it really is just a bunch of questions, several questions, asking you to kind of ascertain your progress so far. It shows you the assignments that you should have finished by this point in the semester. You're just going to put a checkbox next to each one that you actually have finished, just to gauge your progress and see that you are keeping up with the work. And then it also asks you, if the semester were to end today, which could happen if you are, let's say, at a university that got flooded in Florida. Some of them, might have been heavily damaged, and so they might just have to say, that's it. We can't teach any more classes. The semester is just going to be done at this point. So whatever grade you've got in the class now is the grade you're going to get. And so I'm just asking you, like, if the semester were to end today, what grade do you think you would have gotten based upon the work and the quality of the work that you've done? We'll have another one of those around week 12, week 11 or so, and then there will be one at the very end. So please do that in the next week or so. All right? Well, have a great day, everyone. I will see you in a week, and good luck on the CSI assignment. And again, if you have questions, of course, there'll be places, there'll be actually, I'll probably open up a discussion area for you to ask questions about that as well. And then look next Wednesday for some hints about how to do the assignment.
Are you having office hours after this?
Yes.
All right.
So it'll be in a different Zoom session. So we'll end this
Sure.
one and then start the new one. Okay? All right. Take care, everyone. Have a great week.
Yeah.
Bye-bye.
Record.
Same thing for the YouTube folks. Sounds like I got a student who wants to ask some questions, so I will end this stream, and then we will be back next week. Take care, you all. Have a great day. Stay safe. Get some sleep. Take care. Bye-bye.